In 1989, a team of astronomers released a map. Not a map of a country, not a map of a continent, not even a map of the Earth, a map of the universe, a slice through space, a thin wedge of the cosmos, showing the positions of thousands of galaxies across hundreds of millions of light-years. The astronomers expected the galaxies to be distributed roughly randomly, scattered through space the way dust scatters through a room, not perfectly uniform, but without any large-scale pattern. A cosmic scatter plot. What they found instead stopped them cold. The galaxies were not scattered randomly. They were arranged in a structure, an enormous three-dimensional structure of filaments and sheets and nodes and voids, stretching across hundreds of millions of light-years, that looked with extraordinary precision like a single object, like a web. The astronomers, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, had discovered the cosmic web, the largest structure in the observable universe, the skeleton on which every galaxy, every star, every planet, every living thing is arranged. And when the first complete maps were published, when the full three-dimensional structure of the universe was rendered in images, the reaction of almost everyone who saw them was the same. It looks like a brain. The filaments of dark matter connecting galaxy clusters at their nodes, the vast empty voids between them. The overall structure, complex, hierarchical, interconnected, bears a resemblance to the neural networks of the human brain that is so striking that scientists have formally studied the comparison. The largest structure in the universe looks like the most complex structure we know of, and understanding it, understanding how it formed, what it is made of, what it tells us about the nature of the universe, is one of the greatest stories in the history of astronomy. Before we understand what the cosmic web is, we need to understand its scale, and its scale is genuinely, almost uncomfortably large. Start close. Our Milky Way galaxy, 100,000 light-years across, containing somewhere between 200 and 400 billion stars, is a single point on the cosmic web. A node. One of trillions, the Milky Way is part of a group of galaxies called the local group. Approximately 54 galaxies, spread across a region roughly 10 million light-years across. The two largest members, the Milky Way and the Andromeda Galaxy, dominate the group, orbiting each other across 2.5 million light-years of space. The local group is itself part of a larger structure, the Virgo supercluster, also called Laniakea. Laniakea is a supercluster of galaxies, a collection of galaxy groups and clusters bound together by gravity, stretching approximately 500 million light-years across, and containing the mass of approximately 100 million billion suns. The Milky Way, the local group, Laniakea, each one nested within the other, each one larger than the last by factors that stretch intuition to its breaking point. And Laniakea is one supercluster among many. The observable universe contains approximately 10 million superclusters, each one a vast structure of hundreds or thousands of galaxies, each one a node or a section of filament in the cosmic web. The filaments of the cosmic web, the great strings of galaxies connecting the nodes, are typically tens to hundreds of millions of light-years long. Some of the largest known filaments stretch over 1 billion light-years. The voids, the vast empty regions between the filaments, are typically hundreds of millions of light-years across. The largest known void, the Boötes void, discovered in 1981, is approximately 330 million light-years in diameter. If the Milky Way were at the center of the Botas void, the nearest galaxy would be too faint to see with the naked eye from any planet in our galaxy. 330 million light-years of almost nothing. And the Botas void is just one void among thousands. The cosmic web fills the observable universe, 93 billion light-years across, with a structure so large that our most powerful telescopes only show us a portion of it. The full extent of the web extends beyond what we can observe, beyond the cosmic horizon, into regions from which no light has yet reached us. We are not just living in the universe, we are living inside one tiny node of the largest structure that has ever existed. The cosmic web did not always exist. In the first hundreds of thousands of years after the Big Bang, the universe was almost perfectly smooth. The cosmic microwave background, the ancient light released at recombination, shows us this early universe in extraordinary detail. And what it shows is a universe that is uniform to 1 part in 100,000. 1 part in 100,000. Imagine a sheet of paper so flat that the tallest bump anywhere on it is 1/100th of a millimeter. That is how smooth the early universe was. And yet, from that extraordinary smoothness, the cosmic web emerged. How? Gravity, dark matter, time, the tiny density fluctuations in the early universe, the 1 part in 100,000 variations that inflation had imprinted on the primordial plasma, were the seeds. Regions that were very slightly denser than average had very slightly more gravity. They attracted matter, both ordinary and dark, from the slightly less dense regions around them. Dark matter, moving slowly and clumping under gravity, was the first to respond. It began to concentrate in the dense regions. As it concentrated, its gravitational pull increased. More matter flowed in. The density contrast grew. Over hundreds of millions of years, the dark matter assembled into halos, roughly spherical concentrations of dark matter, ranging in mass from dwarf galaxy halos to the enormous cluster halos that weigh trillions of solar masses. Ordinary matter, gas, followed the dark matter. It fell into the dark matter halos, compressed, heated, cooled, and condensed into stars. The first galaxies formed at the centers of dark matter halos. But the halos themselves were not isolated. They were connected. The geometry of the initial density fluctuations, shaped by inflation, by the acoustic oscillations of the early universe plasma, by the distribution of dark matter, was not random. It had a specific structure. Regions of higher density formed sheets and filaments, pancake-like structures and elongated bridges connecting the densest regions. Dark matter assembled first into sheets, then the sheets folded and collapsed into filaments, and the filaments flowed into the densest nodes, the clusters. This process, the formation of cosmic structure from tiny initial fluctuations driven by dark matter gravity, is called hierarchical structure formation. Small structures form first, then merge into larger ones. Dwarf galaxies merge into larger galaxies. Galaxies cluster into groups. Groups fall into clusters. Clusters connect through filaments into superclusters. The cosmic web is the endpoint of this process. The structure that emerges when you take a nearly smooth early universe, add dark matter, add gravity, and wait 13.8 billion years. And it matches, with extraordinary precision, the predictions of our cosmological models. Computer simulations that start with the initial conditions revealed by the CMB and evolve forward in time according to the laws of physics, incorporating dark matter, dark energy, and ordinary matter produce a cosmic web that is almost indistinguishable from the one we observe. The simulations work. The theory works. The cosmic web is exactly what physics predicts should emerge from the Big Bang. And it looks like a brain. The filaments of the cosmic web are among the largest coherent structures in the universe. They are not empty. They are filled with galaxies, with gas, with dark matter, strung along their length like beads on a string. Galaxies that formed in the filaments tend to be drawn toward the nodes, the clusters, at the ends of the filaments. The filaments are not static structures. They are highways. Matter flows along them, carried by gravity, toward the dense clusters at the nodes. The most spectacular known filament is the Hercules Corona Borealis Great Wall, a structure discovered in 2013 and subsequently refined in size to approximately 10 billion light-years across. 10 billion light-years. The observable universe is 93 billion light-years across. The Hercules Corona Borealis Great Wall spans roughly 10% of the observable universe in one direction. Whether it is a single coherent structure, a true filament, or an alignment of multiple structures is debated. The statistics are challenging at such enormous scales, but it represents the extreme end of what the cosmic web produces. More certain and better characterized is the Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey. Approximately 1.4 billion light-years long, the largest structure clearly confirmed at the time of its discovery, subsequently superseded by even larger candidates. And then there is the cold spot supervoid, a vast region of the cosmic web's void network, approximately 1.8 billion light-years across. That may be connected to the cold spot anomaly in the CMB that we discussed in our Observable Universe video. The filaments are not just beautiful. They are scientifically extraordinarily important. The gas in the filaments, called the warm-hot intergalactic medium, or WIM, contains a significant fraction of all the ordinary matter in the universe. When astronomers added up all the ordinary matter they could see in galaxies and galaxy clusters, they found only about half of what should exist based on Big Bang nucleosynthesis predictions. The missing baryons, the missing ordinary matter, were hiding in the filaments. In gas too hot to emit visible light, but detectable in X-rays and in the absorption of background quasar light. The warm-hot intergalactic medium, threading the filaments of the cosmic web. In 2020, astronomers using the XMM Newton X-ray telescope detected the WHIM in a filament between two galaxy clusters, Abell 222 and Abell 223, providing direct observational confirmation of matter in the cosmic web filaments. The filaments are not just scaffolding, they are reservoirs, the universe's hidden inventory of ordinary matter stored in the threads of the web. If the filaments and nodes of the cosmic web are remarkable, the voids are perhaps even more so. The voids are the spaces between the filaments, the vast, dark, almost empty regions that make up most of the volume of the universe. Most of the volume. The cosmic web, for all its dramatic structure, is largely empty. The filaments and nodes containing all the galaxies and most of the matter occupy only a small fraction of the universe's total volume. The voids occupy the rest. Approximately 80% of the universe's volume is void, not completely empty. There are occasional stray galaxies in the voids, isolated and lonely, far from the density of the filaments. But compared to the richness of the cosmic web's nodes and filaments, the voids are effectively empty. Dark, cold, expanding, and the voids are growing. As the universe expands, driven by dark energy, the voids grow larger. The filaments that bound them are being stretched. The clusters at the nodes are being carried further from each other. Dark energy is not just expanding the universe uniformly, it is emptying the voids, draining them of the last stray galaxies, as those galaxies are gravitationally attracted to the nearby filaments and nodes. In the very deep future, hundreds of billions of years from now, the voids will be even more dominant. The cosmic web will be sparser. The filaments will be stretched thinner. The nodes will be more isolated from each other. The universe is becoming more web-like, but a web with fewer strands. Dark energy is slowly dissolving the cosmic web. But the voids are not just passive, empty spaces. They have gravitational effects. A void, by definition, contains less matter than the surrounding regions. This means the gravitational pull inside a void is weaker than outside. Objects near a void, galaxies at the edge of the void, for example, experience a slight net push outward. The matter outside the void pulls them away from the void center more strongly than the sparse matter inside the void pulls them toward it. This effect, the void's gravitational influence, can be measured, and it provides an independent way to study dark energy. The rate at which voids grow, how fast the cosmic web drains matter from them, depends on the balance between gravity and dark energy. By measuring void sizes and their growth rates in galaxy surveys, cosmologists can constrain the equation of state of dark energy independently of supernovae and CMB measurements. Void cosmology is one of the most exciting new frontiers in the study of dark energy. The emptiest places in the universe are teaching us about the force that controls the universe's fate. In 2020, a paper published in Frontiers in Physics made a comparison that captured the imagination of scientists and the public alike. The authors, Franco Vazza, a cosmologist at the University of Bologna, and Alberto Feletti, a neuroscientist, formally compared the structure of the cosmic web to the structure of the human brain's neural network. Their comparison was not metaphorical, it was quantitative. They analyzed the statistical properties of both structures, the distribution of matter in a simulated cosmic web, and the distribution of neurons in a slice of human cerebral cortex, and compared them using rigorous mathematical tools. The results were striking. Both systems show a similar level of complexity. Both are organized hierarchically, small structures connecting into larger ones. Both have a similar distribution of connections. Most nodes have few connections, a small number of nodes have many. Both have similar clustering properties. Both have similar power spectra, the mathematical description of how structure varies across different scales. The cosmic web and the human brain are not the same thing. They operate through completely different physical mechanisms, gravity and dark matter versus electrochemical signals and synaptic connections. They exist at scales that differ by a factor of roughly 10 to the power of 27. But their structural properties, the way they are organized, the way connections are distributed, the statistical signatures of their complexity, are remarkably similar. Why? The most likely answer is that both systems are examples of complex networks that have evolved, or in the case of the cosmic web, assembled through physical processes, to efficiently transmit information or matter across their extent. Networks that need to connect many nodes efficiently tend to develop similar structural properties regardless of the physical mechanism underlying them. The cosmic web and the brain are not related. They did not evolve from a common ancestor. They are not made of similar stuff. But they solved a similar problem: how to connect many nodes efficiently in a limited space, and arrived at similar solutions. The universe, operating through gravity over billions of years, and evolution, operating through natural selection over millions of years, independently converged on similar network architectures. It is one of the most striking examples of convergence in all of science. And it raises, for some people, a deeper question, one that physics cannot answer but that human beings seem unable not to ask. Is the resemblance meaningful? Is there something about the universe, about the laws that govern it, about the way complexity organizes itself at every scale, that makes the brain and the cosmos echoes of each other? Physics has no answer. The resemblance is statistical, not fundamental. It does not imply that the universe is conscious. It does not imply that the brain is cosmological. But it is extraordinary. And it is real. Our understanding of the cosmic web has been built through a series of increasingly ambitious surveys, systematic efforts to map the positions of galaxies across enormous volumes of the universe. The first hints came from small surveys in the 1970s and 1980s. The CFA Redshift survey, the survey that produced the 1989 map that revealed the cosmic web, covered a relatively small volume but showed, for the first time, the filamentary structure of galaxy distribution. The 2DF Galaxy Redshift survey, completed in the early 2000s using the Anglo-Australian telescope, measured the redshifts of approximately 200,000 galaxies, producing a three-dimensional map of the universe across 2 billion light-years. It confirmed the cosmic web structure on larger scales and measured the baryon acoustic oscillations, the cosmic standard ruler, for the first time in the galaxy distribution. The Sloan Digital Sky Survey, SDSS, launched in 2000 and continuing today in various phases, has measured the positions and properties of hundreds of millions of galaxies, quasars, and stars. It produced the first detailed three-dimensional maps of the cosmic web across billions of light-years, including the discovery of the Sloan Great Wall. The images produced from SDSS data, the three-dimensional renderings of the cosmic web, have become some of the most iconic images in modern astronomy. Filaments of galaxies stretching across the screen, nodes glowing at their intersections, voids dark and vast between them, and now the next generation. DESI, the Dark Energy Spectroscopic Instrument, is measuring the redshifts of approximately 40 million galaxies and quasars over its 5-year survey. When complete, it will produce the largest three-dimensional map of the universe ever made, extending to redshifts of over 3, looking back more than 11 billion years in cosmic time. Euclid will map the shapes of 1.5 billion galaxies across 10 billion years of cosmic history. The Vera Rubin Observatory will image the entire southern sky every few nights for 10 years, building up an extraordinarily deep and complete map of the nearby universe. These surveys will not just map the cosmic web with unprecedented precision. They will reveal how the web has evolved over cosmic time, how the filaments grew, how the voids emptied, how dark energy affected the growth of structure across billions of years. They will give us the most complete picture of the universe's large-scale structure ever assembled. And in that picture, in the most detailed map ever made of the largest structure in existence, the answers to some of the deepest questions in cosmology may be waiting. The cosmic web is not just a beautiful large-scale structure. It shapes the properties of the galaxies within it. Where a galaxy sits in the cosmic web, whether it is in a dense node, along a filament, or isolated in a void, profoundly affects its evolution, its star formation rate, its morphology, its color, its size, its fate. Galaxies in dense cluster environments, the nodes of the cosmic web, tend to be elliptical, red, old, containing little gas and forming few new stars. The intense environment of the cluster, the gravitational interactions with other galaxies, the hot gas that fills the cluster, the frequent mergers and close encounters, strips galaxies of their gas, quenches their star formation, and transforms them from spiral galaxies into ellipticals. Galaxies in the filaments tend to be intermediate, still forming some stars, still containing gas, but showing signs of the environmental effects that will eventually transform them as they fall toward the cluster nodes. Galaxies in the voids tend to be spiral, blue, young, still forming stars, still gas-rich. Isolated from the environmental pressures of the denser regions, they evolve more slowly, retaining the properties of younger galaxies for longer. The cosmic web is a sorting machine. It takes galaxies, formed from the same basic ingredients, the same dark matter halos, the same initial conditions, and sorts them by environment. Dense regions produce old red ellipticals. Empty regions preserve young blue spirals. The filaments show the transition between these extremes. This environmental dependence of galaxy properties, called galaxy conformity or large-scale environment effects, is one of the most active areas of galaxy evolution research. Understanding exactly how the cosmic web shapes galaxies, through what physical mechanisms, on what timescales, with what consequences, is a central goal of observational and theoretical galaxy evolution. And it has implications for our own existence. The Milky Way sits in the local group, a relatively modest structure in a quiet region of the cosmic web. Not in a dense cluster, not in a void, somewhere in between. This intermediate environment may be important for our existence. Dense cluster environments are hostile to the development of complex life. Frequent galaxy mergers disrupt planetary orbits. Quasar activity from active galactic nuclei floods the environment with radiation. The hot cluster gas prevents the cool gas accretion that feeds star formation. The quiet filament environment of the local group, rich enough in matter to form galaxies and stars, but gentle enough to allow stable, long-lived stars like our Sun to form and persist for billions of years, may be a prerequisite for life. The cosmic web may not just be the structure of the universe, it may be the reason we are here to study it. Everything we have described, the filaments, the nodes, the voids, the galaxies strung along the web, is the visible part, the luminous matter, the part that emits light. But the cosmic web has an invisible skeleton, dark matter. The filaments and nodes of the cosmic web are not primarily made of galaxies. They are primarily made of dark matter. The galaxies, for all their brilliance, are tracers. They light up the dark matter structure the way Christmas lights illuminate a wire frame. The true structure is the dark matter. The galaxies simply show us where it is. The dark matter halos of individual galaxies are connected by dark matter filaments. The cluster-scale halos at the nodes are the densest concentrations of dark matter in the universe. The voids are regions where dark matter is sparse. The dark matter has flowed out of them, drawn by gravity toward the filaments and nodes. The entire cosmic web, as seen in galaxy surveys, as mapped by gravitational lensing, as modeled in computer simulations, is a map of the dark matter distribution. And dark matter has been assembling this structure since the beginning. In the earliest moments after the Big Bang, dark matter began to cluster. It was the first component of the universe to respond to the tiny density fluctuations seeded by inflation. While ordinary matter was still coupled to radiation, prevented from clumping by the pressure of the photon baryon plasma, dark matter was already assembling into halos. By the time ordinary matter decoupled from radiation at recombination, 380,000 years after the Big Bang, the dark matter web was already beginning to form. It provided the gravitational scaffolding into which ordinary matter subsequently fell. Without dark matter, there would be no cosmic web. The ordinary matter alone, 5% of the universe's energy content, could not have clumped fast enough, in the time available since the Big Bang, to produce the structures we observe. The gravitational pull of ordinary matter alone is insufficient to have assembled galaxies, clusters, and filaments in the time available. Dark matter is what made the cosmic web possible, and therefore dark matter is what made galaxies possible, stars possible, planets possible, life possible. The invisible substance we have never directly detected, the mysterious 27% of the universe whose nature we do not know, is the reason the universe has structure. The reason it is not a featureless, uniform expanse of gas slowly thinning out into the dark. The cosmic web is dark matter's greatest achievement, and we are living inside it. The cosmic web will not last forever. Dark energy, the force we explored in our previous video, is working against it. As the universe expands and accelerates, the distances between the nodes of the cosmic web grow. The filaments stretch. The web becomes sparser. In approximately 150 billion years, roughly 10 times the current age of the universe, every galaxy beyond our local group will have crossed the cosmic event horizon. The cosmic web, as seen from our vantage point, will have become invisible. The filaments will be beyond our reach. The nodes will be beyond our sight. The Milky Way and Andromeda, by then merged into a single elliptical galaxy, which astronomers have nicknamed Milkomeda, will be the only significant structure we can observe, surrounded by the dwarf galaxies of the local group, and beyond that, nothing visible. Future civilizations in that era, if any exist, will have no way of knowing that the universe contains trillions of other galaxies. No light from those galaxies will reach them, no signal, no evidence. They will look out at a universe that appears to contain only one galaxy, and they will be wrong. The cosmic web will still be there, beyond the horizon. Every galaxy, every filament, every cluster, every void, still existing, still expanding, still dark matter dominated at the nodes, still slowly draining into darker states, but invisible, inaccessible, unknowable. We are extraordinarily lucky to live at this moment, early enough in cosmic history that the web is still visible, that we can still see its structure, that the light from distant galaxies is still reaching us, that the evidence for the cosmic web is still written in the sky. In 1 billion years, let alone 100 billion, the sky will look different, simpler, less rich. The window through which the cosmic web is visible is open now, and we are using it. The cosmic web is the answer to a question so large that most people never think to ask it. Why does the universe look the way it does? Why are galaxies not scattered randomly through space? Why do they cluster in groups and clusters and superclusters? Why are there vast, empty voids? Why do the filaments trace exactly the patterns they do? The answer is gravity, dark matter, inflation, time. The precise initial conditions of the Big Bang evolved forward through 13.8 billion years of physical process. The cosmic web is not arbitrary. It is not random. It is the necessary consequence of the laws of physics applied to a nearly smooth early universe. If you know the initial conditions, the amplitude and spectrum of the density fluctuations seeded by inflation, and you know the composition of the universe, dark matter, ordinary matter, dark energy, and you apply the laws of gravity and fluid dynamics and thermodynamics and radiation physics, you get the cosmic web. Every time, the computer simulations that produce the cosmic web, simulations like the Millennium Simulation, Illustris TNG, and the Eagle Project, are among the greatest achievements of computational science. They take the known physics of the universe and run it forward in time, tracking billions of particles through billions of years of cosmic evolution. And they produce a cosmic web that matches the observed universe with extraordinary fidelity. The large-scale structure, the distribution of galaxy sizes and types, the baryon acoustic oscillations, the void statistics, the cluster mass function, all of it matches. The universe is doing exactly what the laws of physics predict it should do, and the cosmic web is the proof. It is the most direct, most beautiful, most comprehensive confirmation that our understanding of the universe, of inflation, of dark matter, of gravity, of the Big Bang, is essentially correct. Not complete, not final, full of gaps and uncertainties and open questions, but essentially correct. The universe is telling us our story is right, and it is telling us in the largest handwriting that exists. In 1989, Margaret Geller and John Huchra released their map, a slice of the universe, thousands of galaxies, a structure nobody expected, a web. 35 years later, we have mapped hundreds of millions of galaxies. We have simulated the entire observable universe in supercomputers. We have measured the baryon acoustic oscillations frozen into the web's structure. We have detected the warm, hot intergalactic medium in the filaments. We have found the missing baryons. We have traced the evolution of the web across billions of years of cosmic time. And still, every time a new rendering of the cosmic web is released, people stop and stare. Because it is beautiful. Not just scientifically significant, not just theoretically important. Beautiful. The filaments glowing, the nodes brilliant, the voids dark and vast between them, the whole structure stretching across the observable universe like something alive, like something that thinks. The resemblance to a brain is not the point. The point is the structure itself. The point is that this vast, complex, hierarchical web of dark matter and galaxies and gas and radiation is what the laws of physics produce when applied to a nearly smooth early universe and given 13.8 billion years to run. The universe began as almost nothing, almost perfectly uniform, almost perfectly smooth, and it became this, the cosmic web, the largest structure in the observable universe, the skeleton on which every galaxy is hung, the dark matter architecture built by gravity across cosmic time, the structure inside which stars formed and planets condensed and oceans filled and life emerged and intelligence arose and creatures looked up at the sky and made maps. You are not separate from the cosmic web. You are inside it. You are made of matter that was once part of it, that flowed along its filaments, that condensed in its halos, that was forged in the stars that formed at its nodes. The web built you, and you are looking back at it,